Hello, Math 201. Welcome to today's lecture 4.9 Antiderivatives. And so the name of the lecture should kind of indicate what it will be about. So we know what a derivative is. And so now we're going to talk about antiderivatives, or the opposite of derivatives. And so the idea of differentiation is you have some function f and you find the derivative function. The reverse process called antidifferentiation is also very important. If you have a function, we want to find the antiderivative, which we generally call capital F. And the special relationship between capital F and little f is that the derivative of capital F is little f. And so a function capital F is an antiderivative of little f if the derivative of capital F is little f. So this is the idea. If you have capital F, little f, and f prime, going to the right by differentiation, so d dx takes us from capital F to little f to f prime. And then going backwards, which we're going to learn is this script symbol, the squiggly s dx. This is going to be integration. This is anti-differentiating. So anti-differentiate f prime, you get little f. Anti-differentiate f, you get capital F. And so that's the idea. And so if you know how to derive, you know how to antiderive, basically. So find an antiderivative of f of x equals 2x. So what function is derivative, has derivative 2x? Well, x squared, right? If you take the derivative of x squared, that's 2x. But also if you take the derivative of x squared plus 1, that's also 2x. Or if you take the derivative of x squared minus square root of 4, it's also 2x. So really any constant c, x squared plus a constant, will have derivative 2x. And so this gives us an infinite family of antiderivatives. So if f is an antiderivative of, if capital F is an antiderivative of little f, then all antiderivatives of little f are going to be capital F plus c, where c is called the arbitrary constant. And so remember, capital F antiderivative means that the derivative of capital F is little f. So if you take the derivative of capital F plus a constant, it's the derivative of capital F plus the derivative of the constant, which is f prime plus 0, which is f. And so that means f plus c is also an antiderivative. And so here's an example. So if you have this being an antiderivative, well, then this is an antiderivative too. This is an antiderivative too. That's an antiderivative, because they all have the same slope, right? Their derivatives are all the same. They all have slope 1. And so you get this family of antiderivatives for the function x equals, or f of x equals 1. That family being x plus c. All of these functions are an antiderivative for that function. Similarly, if you had little g of x, this kind of squiggly function, or sorry, capital G of x being this squiggly function right here, then all of these guys who have the same exact slopes at every point, right? The tangents are all the same at all points. They just differ by a constant. And so this is a family of antiderivatives, and they're all just vertical translations of each other, which is true for all of these. If you just kind of vertically translate or add a constant, they're all the same. And so let's do lots of examples of finding antiderivatives. So find all the antiderivatives. So capital F of x. So what function's derivative is 3x squared? Well, x cubed. But we need all of them, and so we do an arbitrary constant. And then let's just double check. If you take the derivative of that, the derivative of that is 3x squared. So check, it works out. How about this one? What is the antiderivative of 1 over 1 plus x squared? Well, what function has derivative of that? We know it's tan inverse, right? Tan inverse of x plus c. And so then to double check, let's just take the derivative of it. The derivative of tan inverse is 1 over 1 plus x squared. So it works out. And then capital F of t is going to be negative cosine of t, right? Because then, and then plus c. Because then the derivative of negative cosine is negative, which is just positive sine of t. And then the derivative of c is that. And so it works. And so the antiderivative of sine of t is actually negative cosine t. Because if you just tried cosine t, if you took the derivative of cosine t, it's negative sine. So it's off by minus sign. And so let's talk about some notation. If capital F of x is an antiderivative of little f of x, then we say the following. The integral, which is an elongated s, of f of x dx is equal to capital F of x plus c. And each one, and so this is what's called an indefinite integral. So that means this is equivalent to an antiderivative. So an indefinite integral is the same thing as an antiderivative. Antiderivative. It's the way we take an antiderivative. And so this is the integral sign. This is what's called the integrand. This is the differential. So it lets us know we're doing it with respect to x. This is the antiderivative, and then this is the constant of integration. It's indefinite because this integral sign has no bounds. We'll learn what it means when it has bounds. And so thus, this means find all antiderivatives of f, and we pronounce this the indefinite integral of f of x dx. So indefinite integral of f of x dx means find all antiderivatives. And so we have the following power rule. So because we know how to take the derivative of x to the p, we know how to take its antiderivative. And so the indefinite integral of x raised to the p dx is just x to the p plus 1 over p plus 1 plus c whenever p is not -1, because if it's -1, if you plugged in that, it would divide by 0. So that doesn't work. So this is the power rule for integrals, and it's the opposite of the power rule for the other ones, right? You add 1 to the exponent and then divide by it. Whereas before we would multiply that down and then subtract 1. And so that's how we do it. And so that's how we show that it is the antiderivative, right? Just take the derivative of this thing and it's x to the p. And so if you take the derivative of this, right, the derivative of that is just p plus 1 times x to the p plus 1 minus 1. And so it ends up being x to the p. And so it works out. And so this is the antiderivative. We also have the constant and sum rule. So if you do an indefinite integral of a constant times a function, you can pull the constant out. And if you take the antiderivative of two functions being added together, you can take their antiderivatives separately. And so let's put all these rules together and try and do this. And so for this one, we can use the sum and the constant rule and then the power rule to get this guy. And so this, by using the sum, power rule, and constant rule, I'm going to just break it up. It's going to be 3x to the 5th plus dx plus the integral of 2 dx minus 5 times the integral, and then this is x to the 1/2 dx. And so now I can take all those separately. So this becomes 3 times x to the 6th over 6 by the power rule, and then plus 2, and then this is x to the 0, and so we add 1 to it and divide by 1, and so this becomes just 2x. And then minus 5, and then this becomes adding 1, x to the 3/2, and then times, divided by 3/2, which is times 2/3. And then plus c, so the arbitrary constant. And if I mean, that's totally a reasonable answer, but if I want to simplify it, it'd be x to the 6th over 2, minus 2x, and then what's that? Minus 10/3 x to the 3/2 plus c. And if I wanted to double check that this is correct, I could take the derivative of it and I bring the 6 down, and that would give me 3x to the 5th. Take the derivative of that. Oh, that should be a plus sign, sorry. Plus. That will be 2. And then take the derivative of that. 3/2 times that gives me -5. And then it's x to the 1/2. And so this works. All right, let's try this guy. So for this one, we're going to want to divide both terms by x squared to simplify things. And so this is going to be the integral of, and I'm going to bring the 4 out. And so it'll be x to the 17th power, and then dx minus, and then bring the constant out, 5. And then x to the -8 divided by x squared is x to the -10 dx. And now I can use the power rule. So it's 4x to the 18th over 18 minus 5x to the, when we add 1, it's x to the -9 divided by -9 plus c. And that's a totally reasonable answer, so we'll just leave it like that. And then finally, this one, as it's written, we cannot use, because it's having something times each other, so it's not quite the sum rule. And so we need to actually FOIL it first. So foiling it out first, we get 2z cubed plus 2z, and then minus 5z squared minus 5dz. And now I'm going to skip the step where I kind of break it up and just know that I can do each one of these integrals separately. And so this becomes 2z to the fourth over 4 plus 2z squared over 2 minus 5z cubed over 3 minus 5z plus c. If I really wanted to simplify it, I could. It's z to the fourth over 2 plus z squared minus 5/3 z cubed minus 5z plus c. And that's the antiderivative. And so whenever you see things where you can't just do the power rule, we are going to just simplify it out so we can. And let's do some indefinite integrals using trig functions. So what's the antiderivative of secant squared? Well, we know that the derivative of tangent is secant squared. So this has to be tangent x and then plus c. To do this one, this is going to be the antiderivative of 2x dx plus 3 times the antiderivative of cosine x dx, right? Using the sum rule, which that's just equal to x squared, and then plus 3 and the antiderivative of cosine x. So what function is derivative of cosine x? Well, that's just sine x plus c. And you can double check that if you took the derivative of this, that it would be that, and it is. So we're good. And then finally for c, what can we do? So sine over cosine squared. So as it's written, I don't really know a function whose derivative is that, but I can rewrite this as the integral of, well, sine over cosine is tangent, and then 1 over cosine is secant. So just using the trig identities, and then we know that that is actually the antiderivative of secant x. So this is secant x plus c, because the derivative of secant x is tangent x secant x. And so that's a clever way to do that one. And so here's a table of a lot of indefinite trig integrals. So because the derivative of sine of x is cosine x, that means the antiderivative of cosine x is sine of x. Because the derivative of cosine x is negative sine x, the antiderivative of sine x is negative cosine x, so on and so forth. And so those are the rules. And so let's use those rules to do some others. So pulling out the constants, this is 2 pi integral of sine of x dx minus 2, then the integral of cosecant squared x dx. But looking at the table, the antiderivative of sine of x is negative cosine, and the antiderivative of cosecant squared is negative cotangent. And so this becomes 2 pi and then negative, so pi, cosine x, and then minus 2 times negative cotangent x plus c, which is plus 2, but I guess I can rewrite that. So it's negative 2 pi cosine x plus 2 cotangent x plus c. And if you took the derivative of that, the derivative of that would be 2 pi sine, because the negatives would cancel out, and the derivative of that would be negative 2 and then cosecant squared x, so it works. This one, we're going to want to break it up. Whenever you have a division by one thing, you want to break it up into two things so that we can actually divide. And so this becomes the integral of 4 cosine x over sine squared x plus sine squared x over sine squared x. And then I'll just break it up into two integrals. This one, we're going to use that trick as before. This becomes the integral of 4, rewriting it in terms of secant or cosecant and cotangent. This is going to be 4 cotangent x cosecant x dx plus, and then this is just the integral of 1 dx. And so the antiderivative of cotangent cosecant is negative cosecant. So this becomes negative 4 cosecant x, and then plus x d plus 1. Sorry, plus c. And so that's the answer. Equals that. And here's some other antiderivatives we know, or indefinite integrals we know, because of integrals we know, right? So if we know the integral of, or the derivative of e of x, then the antiderivative of e of x is just e of x. The derivative of ln of absolute value of x is 1 over x. So the antiderivative 1 over x is ln of absolute value of x. Another way to say this is the power rule when power is -1 is ln of absolute value of x. And then we know sine inverse, tan inverse, and secant inverse as well. And so let's use these guys. And so this one, breaking it up, this will be 4/3 integral x cubed over x squared, which is just x dx, plus 2/3 integral of 1 over x dx. And so then this becomes 4/3 x squared over 2, plus this becomes 2/3 and then ln absolute value of x plus c. And so that's that one. To do this one it looks like it will match the tangent inverse, perhaps. So this one's actually pretty tricky. So what we're going to do is we're going to do what's called long division, because that term matches that term. And so this is actually going to be the integral of, so I want to produce a 4 plus 4x squared on the bottom so that it will cancel out with that on top. And so let's rewrite this as 4x squared plus 4. But how do we get that to be on top to equal 5x squared? Well, I need to be plus an x squared and then minus 4. So that will add up to be what's on top. That adds up to be 5x squared, and the bottom is 4 plus 4x squared. And then what we can do is we can break this up into two separate things. Is that what I want? I need it to be, because that will give me 1, and then, oh, but I need it actually in multiples of, so that's almost what I want to do. So actually, I think the best thing to do is just do long division. And so let me remind you how to do long division. So long division is this. So I put a 5x squared here, and I want to divide by 4x squared plus 4. So what do I multiply that? And so actually, I think the easiest thing, so I could do long division, but these numbers, those 5s and those 4s, I can pull that out. And so let me just pull that out. It'll make it look much better. So this is x squared over 1 plus x squared, which almost looks like it's inverse tangent, but there's this x squared on top. And so what we're going to do is we're going to do this clever trick. We're going to add 1 and subtract 1. So this is going to equal 5/4. 5/4, and then integral, it will be x squared plus 1 minus 1. And you might ask, well, why am I doing that? Well, the reason is because then this just becomes a 1, and then this is an arctangent. And so that's the trick. And so this will become 5/4 integral of 1 dx, and then minus distributing that 5/4, and it'll be 1 over 1 plus x squared dx. So let me move this over so I have more space. And so, yeah, that's a pretty clever trick, but one that is worth knowing because it happens quite often. And so now we can integrate each one of these. So this is 5/4 x, and then minus 5/4 tan inverse of x plus c. And so that is the antiderivative. So that one's pretty tricky. All right, last thing we're going to do is talk about the intro to differential equations. So a differential equation, all that is just an equation involving a derivative. And so the basic idea of a differential equation is you have the derivative is some function, and you have an initial condition. So like f of a is b. So this is the initial condition, that's the differential equation. And the differential equation with an initial condition is called an initial value problem. And we want to find a particular antiderivative that satisfies both these. So we want to find the antiderivative little f such that its derivative is g of x, this function that we're given in the differential equation. And we want it so that the constant that we plug in, if you plug in a, gives you b. And so I think the easiest thing to do is to do an example. And so let's do this example right here. So I want a function whose derivative is x squared minus 2x, and I want it to be the particular one that if you plug in 1, you get 1/3. Well, the way we do that is we're going to take the antiderivative of both sides. So take the indefinite integral of both sides. The indefinite integral of this is going to be little f of x, and the indefinite integral of that is something we can actually solve for. And so that's what we do. So little f of x is going to be the antiderivative of f prime of x, which f prime of x is x squared minus 2x. So we take the antiderivative of that. But that one, using the power rules, is x cubed over 3 minus x squared plus c. So this is the general antiderivative of that function, but we want the particular one that passes through that point. So how do we find that? Well, you plug in 1 for x. And so if you plug in 1 for x, you get 1/3 minus 1. And we set it equal to 1/3. So this is the initial condition right here. So that's the initial condition. So f of 1 is 1/3. So plug in 1 into this function. You get 1 cubed minus 3 over minus 1 squared plus c equals 1/3. That is what f of 1 is. Because if you plug in 1 into that function, that's what that is. Set those two things equal to each other, and then solve for c, and you get c is just 1. And so that means our final answer is this. This is the function whose derivative is x squared minus 2x, and whose value, if you plug in 1, is equal to 1/3. So that's the one. Let's do one final example. This time, we're going to have a second derivative equal something, and I'm going to have 2 initial conditions. And so how do I do this? So f prime of t is going to be equal to the antiderivative of f double prime of t dt, which that's just equal to the antiderivative of 1 minus, and then I'm going to rewrite this as t to the negative 2 dt. But that's just t, and then minus t to the minus 1 over negative 1, which is t plus 1 over t, and then plus a constant c. And then f of t is the antiderivative of that, which is t plus 1 over t plus c dt. You take the antiderivative of that, you get t squared over 2 plus natural log of absolute value of t, and then plus ct, because that's the antiderivative of the constant, and then plus d. And so now we have all of these things, and we have these initial conditions. And so let's use those initial conditions. And so if f prime of 0 is equal, oh, actually it can't be 0 because that won't work. Let me make this f prime of 1 equals 3. So, because if you plugged in 0, it wouldn't work. F prime of 1, so f prime of 1 is equal to 1 plus 1 over 1, just plugging in, plus c, but by the initial condition, that's equal to 3. And so that means c is equal to 1. And so that means little f of t now is t squared over 2 plus natural log of absolute value of t plus, let's see, plus 1, c is 1, so t plus d. And now we can plug in this initial condition that f of 1 is 0. So f of 1, which is 1 over half plus ln of 1, which ln of 1 is 0, plus 1 plus d is equal to 0. And so this becomes 1/2 plus 1 plus d equals 0. And so d has to equal negative 3/2. And so we have our final answer. So that the function that satisfies this differential equation is t squared over 2 plus ln absolute value of t plus t minus 3/2. So that is that. And that should get you everything you need for the homework. All right, take care.